The dot product has many other nice applications. To choose just one, let's try to answer this geometric question. So how much of a vector v points in the direction of some other vector u? So what I'm asking here is, so I'm going to draw this picture as if it's in R2, but this really could be happening in any Euclidean space, Rn. So if we have a vector v and some other vector u, like this, what I'm asking is, if we sort of squashed the vector v down onto u in a perpendicular manner, how much of v would be sort of pointing out like this, right? So you can see that there's this red vector that we're looking for. It's in the direction of u, so it's a scalar multiple of u, and also the way that we've sort of pressed v down onto u, we've done it in a way so that this other side is perpendicular to u, right? Okay, well, so how can we find this bottom side? Well, it's a multiple of u, so this red vector is some multiple of u. Let's write it ku. So all we really need to know is, what is k? What is this scalar, right? So you can see that how much of v points in the direction of u is sort of going to depend on the length of v, the length of u, the angle between these two vectors, right? This angle here, we could call this theta. That's going to be involved, but you know, length of v, length of u, the angle between them, it's starting to sound like the dot product is going to be involved somehow, because those are the ingredients that make the dot product. So at least the geometric formula for the dot product. So as we do the trigonometry to figure out the length of this red side, we're going to have to keep our eyes peeled for the dot product, because we kind of expect that it will show up. Okay, so let's see. The length of this top side is just the magnitude of v. And then the length of this bottom red side that we're looking for is the magnitude of ku, right? And that's the absolute value of k times the magnitude of u. Okay. Just using trigonometry, we can see that the cosine of theta, right, since the sides in this right triangle that we have information about are the side adjacent, the leg of the right triangle adjacent to theta, and then the hypotenuse. So we should be thinking about cosine of theta. So cosine of theta is going to be the length of the bottom side, which is this magnitude of, or absolute value of k times the magnitude of u, divided by the length of the hypotenuse, which is the magnitude of v. Okay. You can see that since we got a cosine of theta, that's looking good for a dot product to show up, because, right, remember in the back of our minds is the fact that v dot u is the magnitude of v times the magnitude of u times the cosine of the angle between them. Well, we can get closer to this showing up just by moving the v to the left-hand side. So magnitude of v cosine theta equals absolute value of k, magnitude of u. Okay, so if we multiply both sides by magnitude of u, then on the left-hand side, so we'll have a magnitude of u here, and on the right-hand side, this magnitude of u is squared, and this makes the dot product show up. So now the left-hand side is just the dot product of v and u. Okay, times absolute value of k times magnitude of u squared. And now we can solve for the magnitude of k. So just divide both sides by magnitude of u squared. So this scalar k that we're looking for, its absolute value is v dot u over the magnitude of u squared. And if you like, you can write this v dot u over u dot u, which is kind of a nice way to write it. But what about the sine of k? So in the way I've drawn it here, k is going to be positive, and that's because v generally points in the direction of u, right? So this red arrow is pointing in the direction of u, and so it's a positive scalar multiple of u. But what if k is negative? Right? It's possible that if v is going this way, say, and u is going that way, then when you press v perpendicularly down onto u, the result actually, it's parallel to u, but it points in the opposite direction. So in this situation, this red arrow is a negative scalar multiple of u. But if we had a negative scalar multiple, then that means this v is pointing generally away from u, and the fact that we get a negative is actually coming from the dot product, right? That this dot product v dot u will be negative if this is the geometric situation, and this dot product will be positive if we're in the first situation. So actually it looks like the absolute value, right? I didn't need this absolute value from the very beginning. The sine of k was actually encoded in this cosine the whole time, so we don't need this absolute value anywhere. So this tells us what our scalar multiple is. It's just v dot u over u dot u. And that means that this vector, ku, that's the vector we were looking for all along, that's just v dot u over u dot u times u. All right. So that's a sort of nice and tidy formula to find how much of a vector points parallel to u. Along with it, we can actually get a really nice formula for this green vector, which is the vector, it's sort of the part of v that's perpendicular to u. You can see it's just v minus the first one. So this green vector, I haven't given it a name yet, so I'll just call it green vector. It's just the vector that we started with minus the portion of v that points in the direction of u. So that's v dot u over u dot u times u. Right? This has to be the right thing for this green vector, because if you add v dot u over u dot u times u to this thing, you'd get v. So, all right. So we were able to find how much of a vector points in the direction of u. The usual name for this, I've been avoiding giving it its name. The usual name for this this vector operation of flattening it down perpendicular onto the vector u, that's called orthogonal projection. And the notation for it is like this. It's proj uv. So this is the projection of v onto the vector u, and here's the formula we just found. Some people write it this way, the component of v that's parallel to u. And then this other vector, the perpendicular part of v, some people call that the orthogonal complement. And also some people write it using this notation, v sub, this symbol is pronounced perp, or perpendicular. So v sub perp, I guess you could call it. So this way of decomposing v gives us a portion parallel to u and a portion perpendicular to u. And of course, the sum of these two is equal to the original vector. So this one is parallel to u, and this one is perpendicular to u. And it turns out this decomposition of v into a vector parallel and a vector perpendicular to u is unique. This is actually the only way to decompose v into two components that are parallel and perpendicular to the vector u. I won't prove that, but it's actually pretty straightforward to prove. Something that's worth proving is, it's sort of a nice exercise in the dot product, is proving that orth uv is perpendicular to u, right? It's supposed to be, so we could check. Well, to prove this, you can just check that the dot product of these two is 0. Right? So I'll leave that as an exercise. So you can just use this formula, right? Put it in here. Use this formula. Put it in here, and use properties of the dot product. All right. Just as an example, let's find the orthogonal projection and complement of this vector v onto this vector u. So for the orthogonal projection, we just need v dot v over u dot u times u. And these are all straightforward to calculate, right? The nice thing about this formula is that even though this denominator is the magnitude of u, it's squared, and so we don't get any messy square roots. So, oh, sorry, this shouldn't be v dot v, it's v dot u. Okay, so v dot u, that's 1 times minus 1, so minus 1, plus 2 times 1, so plus 2, and then plus 3 times negative 1, so minus 3. Right? And then in our denominator, u dot u, and that's going to be 3 times u, so minus 1, 1, minus 1. So it looks like we're going to get 2/3 times minus 1, 1, minus 1. So we could either leave it like this, negative 2/3, right? Yes, negative 2/3. So we could use this minus sign out in front to flip the signs on all these entries. And if you wanted to, you could actually do this scalar product if you find it illuminating. So you get 2/3 minus 2/3 and 1. Okay, and then for the orthogonal complement, that's v perp, we just do v minus v parallel. So let's see, 1 minus 2/3 is 1/3, and then 2 minus negative 2/3, that's 2 plus 2/3, so 6/3, 8/3. And then 3 minus 1, oh, I forgot to do my scalar product. This should be a 2/3. Okay, so 3 minus 2/3 is 7/3. Okay. Notice that if we actually take this v perp and dot it with u, we do get 0. So this formula for getting v perp, it does produce a vector that's perpendicular to u.